Hello, this is the last video of this lecture. I guess this video will be short. I want you to continue to the end, but it was too long in the last video. Uh, so anyhow, we'll consider an application. So far, we considered just a generic parameter and a generic estimator, and just considered theoretical properties of a good estimator. But let's fix the parameter of interest as the true mean. So expected value of x. And usually, the expected value of x is denoted as mu. We use one Greek letter to pretend as if it's a parameter. So when I say expected value of x, first it's too long, and it looks like random because there is x. So it's convenient to denote it as a Greek letter so that it looks like a parameter of interest you are interested in. Anyhow, it's a better notation, simpler notation. And to estimate mu, we usually use the sample average x bar. X bar is a good estimator. Obviously, it's a natural estimator, and there are theoretical properties which say x bar is a good estimator. First, we already learned x bar's expectation is mu, which is expectation of x. Exactly, this is what we want to know, which is the expected value of your estimator, right? So it's nice. And second, standard error is also given by standard deviation of x divided by the square root of the sample size. So standard error itself does not say it is good or bad, but there is a mathematical theory which guarantees that this standard error is the minimum possible. You cannot make an estimator with a smaller standard error than this. So mathematically, x bar is the best estimator for mu. That's a conclusion in this application. In terms of these two criteria, unbiasedness and efficiency, x bar is the best. More formally, we call x bar is the minimum variance unbiased estimator for mu. MVUE. MVUE is common abbreviation for this, which means there is no other unbiased estimator with smaller standard error. So you cannot make another estimator that dominates x bar. So it tells you a simple lesson. Whenever you are estimating the mean, use x bar. There is no reason to think about this. You get the answer. You have the answer. You already have the best choice. Okay, that's the first simple case. And second example, estimation of variance. Now suppose that the parameter of interest is variance of x. And variance is usually denoted by sigma squared. Also, to show that it's a parameter, it's a convention. We use Greek letters for parameters. And then in chapter 4, I taught two formulas. One is the population variance formula, and the other is the sample variance formula. Both are basically on estimators for sigma squared. When you estimate this parameter, you are going to use one of them, right? So they are competing alternatives as an estimator. And remember, the only difference between them was the denominator. If you use n, it's population variance. If you use n-1, it's sample variance formula. And theoretically, their expectations are given by this. So first, the sample variance formula is unbiased. It's unbiased. The sample variance formula is correctly at sigma squared, but which means the population variance formula is not correctly centered. So when you divide the summation by n minus 1, it is unbiased. But you are dividing by n, which is larger than n minus 1, so this result will be smaller, underestimating. So the mean of the population variance formula equals to sigma squared multiplied by something, but that something is smaller than 1. So it means the mean is smaller than the true sigma squared. So the population variance formula is negatively biased. The sample variance formula is unbiased. And this is why the sample variance formula is more commonly used. However, there are other statistical theory that supports the population variance formula in some cases. In a specific contexts, a population variance formula could be better, but that's beyond the scope of this course, so I'm not going to discuss that. And also, I'm not going to discuss the efficiency of these two estimators because their standard error or variances are much more complicated. So I will skip them. Anyhow, already the game is set. At the first step, we learned the sample variance formula is better. So these two examples show what's interesting here is, so we are using the sample average or the sample variance formula without thinking. In chapter 3 and chapter 4, you just take them granted. So obvious, natural. But actually there are some mathematical background which justify them as an estimator. So still, anyhow, your intuition is correct, and they are natural enough without knowing the mathematical results. Still, I think they are good estimators. Anyhow, this is the last slide. We learned structure of statistical inference. It's about contrast between population and sample, and parameter and statistic. And we learned two criteria for good estimators: unbiasedness and efficiency. So they are about the mean and the variance, respectively. And from now on, and one important application of the results is to the mean. So from now on, we are going to consider estimation of the mean only. In the following chapters, you can think about different estimations, but estimation problems, but we are not going to consider them because they are more involved. Understanding the mean is, I think, enough, and delivers all the intuition you need. So I am not going to go beyond it. And what you have to remember here is the sample mean is the best estimator for the population mean, right? I told you why it is mathematically the best, and that's it. That's what we learned in this lecture. And next time, in the next lecture, I am going to extend the structure of the estimator. We will make the estimator more fancy and more useful. Look forward to that, and see you later. Bye.